by nodal analysis. And this week kita sambung second one. Sekejap saya tak ni lagi kah? Saya tak record lagi. Dah record ke?
Dah, sir. Dah record, sir.
Sudah, sir. Sudah.
Okay. So now let's share the slides. We are going to continue with a mesh current method. We have gone through the nodal analysis. Now we are going to the second method, which is mesh analysis. Okay. So if in this nodal analysis we use the KCL, Kirchhoff current law. So in mesh current method or mesh analysis, we use KVL. Basically, the summation of a voltage in a loop is equal to 0. Right? So mesh analysis provides another general procedure for analyzing circuits using mesh current as the circuit variables. Okay. Nodal analysis applies KCL to find unknown voltages in a given circuit, while the mesh current method is developed by applying KVL around meshes in circuits to find unknown currents. And as we know, a mesh is actually a loop, does not contain any other loops within it. So this method basically that using mesh or loops in analyzing your resistive network. Okay. The mesh current method, these are the steps that we are going to use in order to analyze the circuits. First step is basically that you need to assign the mesh around the mesh current in the network by naming I1, I2, and so on. Or you can name it as IB, IA, IB, IC, doesn't matter. As long as your convention is consistent. Then, second step, you apply the KVL to each of the N meshes. So you use Ohm's law to express the voltage in terms of the mesh currents. Then you solve the resulting and simultaneous equations to get the mesh currents. So it's similar to nodal analysis. If it's in nodal analysis, you assign nodes voltage at each node. So you have N nodes, so you have N minus 1. Then you apply, if it's node, you apply KCL and you use Ohm's law in terms of the nodal equation. For mesh, you assign the mesh current, okay, in N meshes. So there is no N minus 1. So it's N meshes. So if you have N meshes, then you have N independent variables, which is in terms of currents. Then you apply the KVL in the mesh analysis to each N meshes, and you use Ohm's law, where you express the voltage in terms of the currents. Then you solve the resulting and simultaneous equation to get the mesh current. So the method is similar to the nodal analysis. The only thing is that whether you use current or voltage, you use KVL or KCL. Right? So let's say you have this, two mesh circuits. In the mesh analysis, to avoid confusion in writing the circuit equation, unknown mesh currents will always define in a clockwise direction. Okay, known mesh currents, i.e. when a current source is present, will always be defined in the direction of the current source. Right? So that is a convention. So let's say you have these circuits, okay? You have this voltage source, then you have R1, R2, R3, R4 connected in such a way that you have two meshes, so I1 and I2. So you put the convention of clockwise. The direction of the current is clockwise. Right? So from here, you can find the I1 and I2 using the mesh analysis. Right? So let's say you have these two meshes, okay, just now. So for the mesh one, you have Vs, okay. Current is basically that going out from the positive terminal. Okay, current is going out from the positive terminal and going in to the resistor to the positive. Going in here, positive, and back there. So that is the flow of the I1. So going out from the positive terminal, Vs, and convention, we put a positive sign. Then going into the resistor, which we call it V1, going into the positive terminal, then the convention is minus. So minus V1. And this one is minus V2. So equal to 0. So the KVL equation is that V1 minus V2, Vs minus V1 minus V2 equal to 0. Basically that the summation of a voltage in a loop is equal to 0. Then we can write using the Ohm's law, V equal to IR, where V1 is actually I1 times R1 here. V2 is actually I1 minus I2. You remember this? I1 is going this way from top to bottom, but I2 is going from bottom to top. So in opposite direction. So therefore, I1 minus I2 times R2. So the resultant of the current flowing through R2 is actually I1 and the combination of I1 and I2. If it's in the different direction, then you subtract. So therefore, the equation of Vs minus V1 minus V2 equal to 0 can be written as Vs minus I1 R1 minus, in the bracket, I1 minus I2, close the bracket, times R2 equal to 0. So this is the first equation that you have. Okay. Now you go into the second mesh. So this second mesh. For the second mesh, you have I2 is actually going into R3 here, going into R4, going into R2. So you don't have any voltage or current source. So the summation of a current in a loop is equal to 0. So starting from R2 here, V2. So current going in, actually you can use all minus sign just to be consistent with the top. So minus V2 minus V3 minus V4 equal to 0. Or V2 plus V3 plus V4 equal to 0. It's the same thing. Where V2 is actually now actually I2 minus I1, because I1 is from a different direction. So I2 minus I1 times R2, and V3 is I2 times R3, and V4 is I2 times R4. Okay. Therefore, it can be written as, in the bracket, I2 minus I1 R times R2 plus I2 R3 plus I2 R4 equal to 0. So you rearrange the equation just now. You rearrange this equation. Okay. And this equation to be written as this. So in the variable is actually I1 and I2. This is the, what we call it, the independent variable. So R1 plus R2 times I1 minus R2 I2 equal to Vs. and minus R2 I1 plus R2 plus R3 plus I4 I2 equal to 0. And you can use simultaneous equation to solve for I1 and I2. Okay, so you can use Cramer's rule to solve this, or you can use a normal simultaneous equation method. Okay, so now we go into an example. So this circuits with independent voltage sources. You have two independent voltage source, which is 36 volts and 24 volts, and you have 5 resistors connected in this way, and you have mesh 1 and mesh 2, right? I1 and I2 through that. So mesh current I1 and I2 are assigned to meshes 1 and 2. It is conventional to assume that each mesh current flows clockwise. You assume that it flows clockwise. So even though I2 basically that you can go this way, anti-clockwise. But this one, you assume that the question actually assume that all are clockwise. So apply KVL to each mesh. Okay. So can you do this? This example. The first equation for the I1, 36 volts minus I1 times 2 minus I1 minus I2 times 12 minus I1 times 4 equal to 0. Dapat? Can you write that?
Yes, sir.
Right? Can you write that?
Yes, sir.
Okay.
Sorry, sir, can you please repeat because I lost at the I1 part.
Okay, 36. Okay, you see this? Current is going out, right? So going out from the positive terminal, we use the convention of positive. So 36 volt, and this one is going to the positive because this is the absorb the energy, right? So going into the positive terminal will be negative. So I1 times 2. So V equal to I1 times 2. Remember IR, V equal to IR. So 36 minus 2I1. And this one going in. So I1 is going in, but you have I2 is going this way. So I1 minus I2 times 12. What about this one? This one is current is this way. So I1 times 4. So all add up equal to 0. Okay. First one, that is first mesh. Second mesh. Second mesh. Where we want to start? Let's say we start here. Okay. Let's say I1 is going out and I2 is going out. So I2 minus I1 times 12. Okay. Minus I2 times 9. Going in here. So minus 24 minus I2 times 3 equal to 0. Okay. You got it?
Of course, sir.
So try to solve that. What is I1? What is I2? Okay. Can you do that on your own? I give you 5 minutes.
Answer.
Then after that, you tell me the answer. Dapat tak?
Nampak sir.
Dapat berapa? Berapa I1? What is I1? What is I2? Dapat tak?
I1.
Ataupun nanti apa ni, I tinggalkan untuk you apa ni, you check. Because after this, you check on your own. Because after this, I'm going to what we call it, maybe tomorrow I'm going to show you a software that you need to use, that you can check, you can do the simulation.
Dapat saya jawapan.
Saya pun tak tahu lagi jawapan. You cari dulu.
Jawapan dia saya dapat I1 sama dengan 4. I3 sama dengan 2.
Betul
I2
ke tak?
sama 3.
Check lah dulu. Okay, I'm not going to tell you. Right?
Okay.
Okay. Example number 8. Problem 3.25 from the Rizzoni textbook, page 120. Using mesh current analysis, find the voltage V across R4 in the circuit shown below. Okay, so from here, how many mesh that you have? 1,
3.
okay,
3.
2, and 3. Okay, you have 3 meshes. Okay, now mesh number 1. Mesh number 1 is basically that 12 volts positive minus V1. What is V1? V1 is basically I1 times R1. This is V1 minus V2. V2 is actually I1 minus I2 times R2. Okay, minus V3, basically I1 minus I3 times R3. Right now, I said 12 minus, right? So here it said minus 12 plus, plus, plus. So basically, just multiply by 1. So basically, depending on the convention. In this example, the convention is that going out negative, going in positive, right? So it does not matter as long as you are consistent. So from here, you substitute the value of R1, R2, and R3 into the equation. Then you got this 50 I1 plus 20 times I1 minus I2 plus 20 times I1 minus I3 is equal to 12. So your first equation is 90 I1 minus 20 I1, 90 I1 minus 20 I2 minus 20 I3 equal to 12. That's the first equation for mesh 1. Then you go into mesh 2. For mesh 2, here, okay, this one. So you have 5 volts, right? So the convention for this example, it uses going into the positive sign is positive, so it's a 5 volt. So minus R4 times I3 minus I2 plus I2 times I1, I2 minus I1 equal to 0. So basically this, right? Okay. Then you substitute the value of R4 and R2 into the equation. So you get 10 times I3 minus I2 minus 20 times I2 minus I1 equal to 5. And you get the second equation, 20 I1 minus 30 I2 plus 10 I3 equal to 5. So this is the second equation from mesh 2. Clear or confused?
Yes, sir.
Clear. Then for mesh 3, so this one, so you have the R3, which is I3. So you have R3 times I3 minus I1 plus R4 times I3 minus I2 plus R5 times I3 equal to 0. Substitute the value of R3, R4, and R5 into the equation. So you get 20 I3 minus I1 plus 10 I3 minus I2 plus 15 I3 equal to 0. So therefore, the third equation that you have is minus 20 I1 minus 10 I2 plus 45 I3 equal to 0. Now you have 3 equations with 3 unknowns. 3 equations with 3 unknowns. So therefore, you can use the simultaneous equation. So you can set up the simultaneous equation just like this, using Kramer into a matrix form. So the first equation was this is the first equation, 90 I1 minus 20 I2 minus 20 I3 equal to 12. The second equation was 20 I1 minus 30 I2 plus 10 I3 equal to 5. And the third equation is minus 20 I1 minus 10 I2 plus 45 I3 equal to 0. So this is the systems of equation that you have for 3 by 3 matrix for simultaneous equation. And you use Cramer's rule. By using Cramer's rule, I1 you can find by determinant of the what do you call it? You substitute this the first column with this 1250, and the second column and third column the same. So this, okay, this and this one actually here. Okay, so divide by the determinant of the original matrix. So you find 127.5 milliamps. Okay, for I1. Clear? How to do this?
Yes, sir.
Then I2. So this remain from the original. This remain from the original. This one actually you take from the 1250. Then you set up like this. Then you do the calculation. You get minus 67.8 milliamps. And the same thing for I3. Right? So this one is from the original matrix. This is from the original matrix. This is from the resultant one. And you divide by that, so you get 41.6 milliamps. Right? So that's the voltage across R4, because the question asks for to find the voltage across the R4. This across the asks you to find the voltage across the R4 here. So you have to calculate that. What is R4? R4 is actually I3 minus I2 times R4. So therefore, you substitute the value of I3, substitute the value of I2, and multiply by 10. So you get 1.09 volts. Right? So the second example, another example. This is example number 9 actually. So problem 3.26 in the textbook. Using mesh current analysis to solve for the voltage V across the current source. Now you want to find the voltage across here, the current source in the in these circuits. So how many what do you call it mesh do you have? 1, 2,
3.
you have 3 mesh. So the first one, so you get 3 volts minus I1 R1 minus R2 times I1 minus I2 equal to 0. So this convention dia pakai minus going out, and this is so terbalikkan daripada apa yang saya cakap. So you get minus 3 plus R1 I1 plus R2 I1 minus I2 equal to 0. So substitute the R1 and R2 into the equation. You get 20 I1 plus 30 times I1 minus I2 equal to 3. So 50 I1 minus 30 I2 equal to 3. So that is the first equation. The second equation from mesh 2 here. So you have R2 times I2 minus I1 plus R3 times I2 plus V, because the voltage is given as V equal to 0. What is V? V is actually equal to what? V is equal to what? This is given by this. Right? This voltage here is V. If the voltage here is V, so therefore it's actually the voltage of here plus the voltage across, here, R4 and R5. So this is actually the voltage of VR5 plus VR4. So what is the voltage VR4? It's actually I3 times R4. What is the voltage across R5? It's actually R5 times I3. So V is actually R4 plus R5 times I3. So equal to 30 plus 20 is 50. So 50 I3. So you substitute this V with this. So you get this. Okay. So R2 you substitute with the value of 30, R3 with the value of 10. So you rearrange the equation, you get minus 30 I1 plus 40 I2 plus 50 I3 equal to 0. Okay. That is mesh 2. For the current source, here 0.5 is actually equal to I3 is actually equal to I3 here minus I2 is 0.5 here. So therefore I3 is equal to I2 plus 0.5. So actually you can substitute here. So now you have two equations and two unknowns. Because I3 is actually this, what I call it, this, you can get from this relationship. I3 equal to I2 plus 0.5. So you substitute, okay, just now, the equation 3 into 2. So you get minus 30 I1 plus 90 I2 equal to minus 25. So you solve the simultaneous equation. So you get this 150 I1 minus 90 I2 equal to 9 and minus 30 I1 plus 90 I2 equal to minus 25. So you have these two equations and you solve. You can add, you get 120 I1 is equal to minus 16. So therefore I1 is equal to minus 133 milliamps. Substitute into the equation 4, you get the value of I2. So you get, now you have already the value of I1 and I2, and I3 you get, you can calculate from I2 plus 0.5. So you get I1, I2, I3. Then from there, you can find a V, the voltage across the current source, which is R4 plus R5 times I3. So 50 I3 equal to 50 times 178 milliamps, so equal to 8.9 volts. So you solve the problem. That is your mesh analysis. Any question on mesh analysis? Simple. And you can get further, what I call it, understanding by doing more exercise. And what I will do is that I will give you the assignments later on this. Okay?
All right, sir.
Okay. So any questions so far on the theory? Any clarification that you need?
For me, it's okay, sir. I don't know for the others. For me, there is okay. No problem.
No problem.
For me.
Okay. And everybody just keep quiet. So I consider they understand.
Alhamdulillah, sir.
Okay. So now we go into the linearity property. Okay. So we have learned about the KCL, KVL, Ohm's law. We learned about the parallel resistors. We learned about series resistors. We learned about nodal analysis. We learned about mesh analysis. Now we are going to go into further methods of analysis. But first, we need to learn about linearity property of the circuits. So it is the property of an element describing a linear relationship between cause and effect. So this is the linearity property. A linear circuit is one whose output is linearly related to its input. So basically that if the relationship between input and output is directly proportional. If you reduce the input, then maybe you whether it's increase inversely or decrease inversely and decrease in the proportionally. A circuit is said to be linear if it's both additive and homogeneous. A linear circuit only consists of linear elements and linear dependent source and linear independent sources. So a circuit is said to be linear if it is additive and homogeneous. So it consists of linear elements, linear dependent sources, and linear independent sources. Okay, these are the properties. Homogeneity, which is scaling property. If an input is multiplied by a constant, therefore the output is multiplied by the same constant. So V equal to IR. So if you reduce or you multiply by the factor K of the input, which is I, so KIR. So therefore the output is also scaled by K. So which is KV equal to KIR. Clear? So the input is basically I. So the output is basically V. So if you scale the I by K, you also scale the output V. Yeah. So that is a homogeneity property of a linear circuit. So additive property. Additive property basically that the response to a sum of inputs is the sum of responses to each input applied separately. Let's say you have a two equation. V1 is equal to I1R and V2 is equal to IR2. So therefore, if you add these two, if you add the I1 and I2, so therefore the voltage also you can add V1 and V2. So V is equal to I1 plus I2R is equal to V1 plus V2. So that is an additive property. So by using that property, we can use to solve our resistive network problem. Let's say we assume V0 is equal to 1 volt. Use linearity to find the actual value of V0 in the circuit shown below. So the answer is V0 equal to 4 volts. So let's say V0 is equal to 1 volt. You assume. So how do you find this? And you can find, use the linearity. What do you call it? Property to find the answer. What is the actual value for V0? How? You find the current first, right? What is the current? If it's V0 equal to 1 volt,
1/8 je, 1/8 ampere.
2.8 ampere. What is the actual current? The actual current.
Equal current, sekejap. Tengah kira. E 20
Kalau
times
guna voltage divider.
Yes. Use the voltage divider or current divider.
5.
Actually, you can use what do you call it, the voltage divider. The whole thing is 10 volts. Okay. The voltage here is 10 volt, right? 10 volt. Okay.
Okay.
So,
What is the ratio of this?
Ratio of
12 and 8.
2/3. 32.
2.4.
What is the ratio?
Between what, sir?
12 and 8.
2/3, sir.
Huh?
2/3. 32.
2 over 3.
Yes, sir.
So if it's 2 here, this is 3 there, right?
Yes, sir.
Right. So if it's this, so if this is 1, this is 1 volt, so this is will be
1.5 volt.
1.5 volt. Okay.
Abang.
So the total is 2.5, right?
Yes, sir.
2.5. But it's actually 10 volt here. So what is the ratio? 2.5 to 10.
1/4.
1/4.
So basically that you need to times this by
4.
4. So what is the answer?
4 volt.
4 volt.
4 volt. So that is the linearity property. Here.
Clear.
Yes, sir.
Okay. So this example just to show that linearity property. So this one is really from the what do you call it, your previous what do you call it, on the property where the voltage across an element parallel to the same voltage as the voltage source. So from there, you use the voltage divider between 12 and 8. And if you assume this is 1, so you tengok dia punya ratio. So that's why you can do that. So that is linearity. So from there, from the linearity properties, now we go into the principle of superposition, where you can analyze a circuit with multiple sources. You can analyze the circuit using one source at a time. Then after that, you add them together. So that is the principle of superposition. So you use the linearity property to do the calculation for the principle of superposition. So a novel method for analyzing circuits with multiple sources. So the superposition theorem states that the voltage across or current through an element in the circuit is the algebraic sum of the voltage across or current through that element due to each independent source acting alone. So maknanya, if a circuit you have two sources, you can do your calculation by using the first source and eliminate the second source. Then after that, you do the analysis by eliminate the first source and do the calculation for the second source, and you add together the result. So that is using the linearity principle, the additive principle. So using the superposition theorem actually use that principle. So the principle of superposition helps us to analyze a linear circuit with more than one independent source by calculating the contribution of each independent source separately. So basically that if you have two independent sources, you analyze your circuit using the first source, and after that using the second source, you add together. So if you have n numbers of sources, therefore you need to do n numbers of calculation. So sebenarnya lagi banyak kerja lah. So the basic concept of superposition method is to analyze a circuit one source at a time. In a linear circuit containing n sources, each branch voltage and current is the sum of n voltages and currents, each of which may be computed by setting all but one source equal to 0 and solving the circuit containing that single source. So you have to do n multiple calculations, actually. To ascertain the contribution of each individual source, all of the other sources first must be turned off, basically set to 0. How are you going to set to 0 all these sources? By replacing all independent voltage source with a short circuit, like this. So basically that this voltage source, when you want to turn this to 0, you short the circuit. So basically Vs equal to 0. That is if you want to turn off the voltage source. If you want to turn off the current source, let's say this is the current source, okay, the source, you set the Is equal to 0. How to set this equal to 0? You take out the current source and leave it open. When it's open, there is no current flowing. So I equal to 0. So you have to remember that. To source I equal to 0. How to make it I equal to 0 is an open circuit. How I want to turn off a voltage source? Vs equal to 0. How to do that? I short the voltage source. Then equal to 0. Remember that. Okay. Steps to apply superposition. Turn off all independent sources except one source. Find the output voltage or current due to that active source using nodal or mesh analysis. Now you see, you have to use what you learned before, mesh or nodal analysis, or voltage divider, current divider, semua pakai. Repeat step 1 for each of the other independent source. Then find the total contribution by adding algebraically all the contribution due to the independent sources. So in the exam, maybe that will give you a question that say, solve these circuits using superposition. So if you use other methods, you get 0. You need to use superposition. If the answer asks you to do calculation based on superposition theorem. If we spell out, if you tell you which method to use, and if you use different method, you get 0. So step to apply superposition, first turn off the independent source except one that you want to do the analysis. Then you use nodal or mesh analysis to do the calculation, solve your problem. Then after that, you turn off that source and you change with another source. Then you repeat doing the mesh or nodal analysis. Finally, you add the contribution of each source. So you need to keep in mind that when we say turn off all other independent sources, basically that the voltage source is replaced by 0 volt short circuit. If it's current source replaced by an open circuit, 0 amps. Dependent sources are left intact because they are controlled by circuit variables. Only the independent source that you turn off. Example. Determine using superposition the voltage across R. So you need to find the voltage here. Find this voltage in the circuit shown below. IB is given as 12 amp. VG given as 12 volts, R is given as 0.23 ohms, RB is 1 ohm, RG is 0.3 ohms. So now, how many independent sources that you have in these circuits? How many?
Two.
Two. Okay. When you have two, and how many times of calculation that you need to do? You need two times of calculation. One, first using the whether it's current source or voltage source, and second, the other one. Let's say you start with current source first. Okay. Let's say you start with the current source first. You specify the ground node and the polarity of the voltage across R. So I have drawn there first. Replace the voltage source with a short circuit because you want to do the analysis using the voltage current source first. You want to do based on this first. Okay. So you have to turn off this. How to turn off this is basically using the short circuit. Then you draw the circuits. So this is what you draw the circuit. This is what happened. So now you use the KCL. So IB is actually equal to, this is IB equal to this I, and this I. Okay. So equal to IB minus VRI. This VRI is basically that the voltage across here, the voltage across VR with respect to the current source. So that's why we have the I here, VR minus I. Actually, this indicator. So with respect, the voltage across resistor with respect to the current source. So the voltage across here divided by RB minus the voltage across RG divided by RG minus the voltage across VR across the resistor equal to 0. So this is the KCL. Okay. And you substitute the value. IB was given just now. Here, IB is 12 amps. RB 1 ohm, RG 0.3, VG is 12, R is 0.23 ohms. So you substitute all the value, you get VR is equal to 1.38 volts. Contribution from the current source. So that is only contribution from the current source. You have two sources. So the second calculation that you need to do is with respect to the voltage source just now that we turn off. So second step, second calculation, you need to do to find the voltage VR with respect to the voltage source. So what you need to do? What you need to do is that to turn off the current source. Okay. To turn off the current source, basically that you replace with an open circuit. So this original circuit here, this original circuit is replaced by this circuit. So now you need to find the voltage R with respect to the contribution from the voltage source. See this? This is V, this is I. Okay. So now, what is the KCL? It's clear that you have the voltage here is that across here is VRV. So the current here is VRV over RB. The current here is actually VRV minus VG divided by RG and plus VRV over R equal to 0. You substitute the value, then you get the VR with respect to the voltage source is equal to 4.61 volts. So now, what do we need to do in order to get VR, the total voltage across this resistor? What do we need to do with these two numbers? Is you add. So you add. Therefore, VR is equal to the voltage contributed by the current source plus the voltage contributed by the voltage source. So equal to 5.99 volts. Okay. So that is the principle of superposition. So note, superposition essentially doubles the work required to solve this problem. Because you need to do twice amount of calculation. Whereas the voltage across R can easily be determined by using a single KCL equations. A single KCL. So if we use a single KCL here, voltage here, so you know that VR here, so IB is equal to VR over RB, VR minus VG over RG minus VR over R. Rearrange the equation, so you get this value by subtracting all the value. See, basically that you double. So superposition method actually doubles the calculation. Or even actually triple, depend on how many number of sources that you have. If you have 2 sources, independent sources, you double. If it's 3 independent sources, you triple. If it's 4 independent sources, what do you call it? Quadruple. So you keep making your you add more work by using superposition. But we need to learn the superposition method, because sometimes it even though it's a lot of calculation, but it make your what do you call it? It enables you to solve a complex problem sometimes. So, example, use superposition theorem to find V in the circuit shown below. So you have a 6 volts. You have 2 resistors, 8 ohm and 4 ohms, and you have a 3 amps source. So basically that you want to find the V there, the voltage across the 4 ohms. Since you have 2 independent sources, so therefore you need to do 2 calculations twice. First, you do with respect to the voltage source. So therefore, you discard the 3 amp source by replacing it with an open circuit. So you zeroize the current source. So the second calculation you need to do with respect to the current source of 3 amps. So therefore, you discard the 6 volt voltage source by zeroize the voltage. Actually, you replace with a short circuits. So you need to do this, these 2 calculation first based on this, and second based on the current source. But if you do this, you can do on your own, you should get an answer of 10 volts. So let me just do what I call it, congak lah. So what is the voltage here across 4 ohms with respect to 6 volt? So you use a voltage divider. What? 6 times 4 divided by 12.
Volts, sir.
How much?
2 volts, sir. 2
Huh?
volts.
2 volts.
Yes.
Yes. 2 volts. So with respect to this, and what about this one? What is the current flowing through the across this one? You use a current divider. So 3 multiplied by 8 divided by 12. Berapa? I3. The 2. 2 multiplied by 4 is 8. So 8 plus 2,
10.
10 volts. So that is the answer. So the voltage V2 here is actually 8 volts. This one is 2. So 8 plus 2 is 10. What about this one? Use the superposition theorem. Find V naught in the circuit below. So the first one, let's say you turn off the current source. What happened? You open this up. So what is the voltage here? So 10, 4 volts. Is that correct?
Yes, sir. 4 volts.
4 volts, sir.
Here, this is 6 volt here. This is 4, right? Right? With respect to this. Let's
Yes, sir.
throw
Yes,
away
sir.
this. The second one, you short this. So 8 this way. So if it's 8, so this is 4. So this is 4. 4 times 2 is 8. So 8 volts. So 8 plus 4,
8 plus 4, 12.
12. Okay. So that is the superposition. Anybody confused by I use the what do you call it? Google Chongak. Okay. Now this one. See this? 8 amp, 20 volt.
Mhm.
Okay. And this is 4, 10. Reduced by half, right?
Yes.
So the
Yes, sir.
answer is
6.
by half. Linearity properties. The calculation is still the same. Okay. So what time is it now?
12, 17,
12:17.
18.
So this is a Thevenin theorem. So basically next week we do the revision and we do examples. So I want to finish the theory first.
Okay.
So Thevenin theorems. When viewed from the load, any network composed of ideal voltage and current source and of linear resistors may be represented by an equivalent circuit consisting of an ideal voltage source VT in series with an equivalent resistance RT. So let's say you have a circuit like this. You have a source and you have a load. So this a load basically can be resistors and whatnot. Can be many resistors here. Can be many resistors here inside here. And you have a source here. So this actually can be represented in the Thevenin circuits. Basically, you have V Thevenin, VT, and R Thevenin, and a load AB. So you get this. So you can represent by this. So a lot of resistors is reduced to this, and the voltage source, the sources reduced to this. It can be, the sources can be current source, can be voltage source. But if you say Thevenin, therefore the representation is that V Thevenin and R Thevenin. Another method is Norton. When viewed from the load, any network composed of ideal voltage and current sources and of linear resistors may be represented by an equivalent circuit consisting of ideal current source IN in parallel with equivalent resistance Rn. So the same circuit, instead of representing by Thevenin equivalent circuit, you can also represent using Norton equivalent circuit. When you say Norton, then basically you have I. You represent by current source parallel with the resistor, Norton resistance. So you see this? If Thevenin is the voltage, Thevenin voltage in series with the Thevenin resistance. Norton current parallel with the Norton resistance. Okay. Rn is actually equal to R Thevenin. The only difference is the IN and VN, IN and V Thevenin. So this is actually, if you want to calculate Norton or Thevenin equivalent resistance. So you use the series resistance and parallel resistance method that you used before this. Whether it's Thevenin or Norton equivalent resistance is the same. So for this, let's say for this example, you have R1, R2, and R3. So for R Thevenin or R Norton, you calculate from here. So if you want to find from this side, so therefore the calculation is from here. So R1 parallel R2 first, then you add with R3. So this R1 parallel R2 plus R3. So this is R Thevenin. So R Thevenin is actually equivalent to R Norton. So RT is equal to Rn. Example. Find the Thevenin equivalent resistance since by the load RL. So this is the load RL. So what is the first step? The first step is basically that you cut off RL. You cut off RL. Then you find the Thevenin resistance. How to find the how to treat this current source and voltage source? Same thing that you zero rise the source as what we use in the superposition. If you want to zero rise the voltage source, what do? Short. If you want to zero rise the current source, what do? Open. So that is the circuits. First, you remove the load. RL you remove. So you get this terminal AB. Second, zero rise all the independent sources. So the voltage source becomes the short. Current source becomes open here. And this voltage source also short here. So you have these circuits, these resistive circuits. Then you calculate. So how do you calculate this? Basically, first one you see, okay, this two is in parallel. So 50 parallel with 100. So you redraw. So you redraw, you get this. So now you can see 50 actually parallel with 100. So this 50 parallel with 100. Then you add with the 50. Okay. So this part. So now you have 50 parallel with this and parallel with 100. So 50 parallel with this part, parallel with this 100. So you do the calculation, you get 23.81 ohms. So this the step. So 50 with 100, you get 33.3. So 50 plus 33.3, so 83.3. So 50 parallel with 83.3, parallel with 100. So you get 23.81 ohms. This is R Thevenin is equal to R Norton. Same. If you want to calculate the Thevenin voltage, the equivalent Thevenin source voltage is equal to the open circuit voltage. So that circuit, just now, you calculate the open circuit present at the load terminal with the load removed. Example, compute the Thevenin voltage in the circuit shown below. So basically that you want to find the Thevenin voltage. Basically, you want to find the voltage here, V Thevenin here. If you want to find the V Thevenin here, you need to first take out the RL, like that. So now you find the open circuit voltage. So V open circuit is equal to V Thevenin. How do you find that? Define the open circuit VOC across the open load terminals. Apply any preferred method to solve for VOC. So the Thevenin voltage is equal, VT is equal to VOC. So you use the voltage divider. So V Thevenin is equal to VOC equal to voltage across R2 is equal to VS. Use the voltage divider, VS times R2 over R1 plus R2. The voltage across R3 is equal to 0 because there is no current flowing. Okay. So that is the V Thevenin for this circuits. If you want to find the IL drawn by the RL, so you source V Thevenin we find already. So now we find the R Thevenin. R Thevenin is basically R1 parallel with R2 plus R3. So therefore, IL is actually, so this whole circuit, this whole circuit, this part can be replaced by this part. See, this is what we call, this is actually Thevenin circuit. Okay, can be replaced by that. So when we replace by that, we can use the voltage divider to find the, or we can use the mesh analysis to find the current across RL. Here. So IL is actually VT over RT plus RL. So this is the V Thevenin. Equal to VS R2 over R1 plus R2 times 1. Yeah. So this is actually IL using the Thevenin method. Okay. This is if you want to compute the Norton current. The Norton equivalent current is equal to the short circuit current that would flow if the load were replaced by a short circuit. Okay. Same circuit just now. Now you want to find the current, Norton current. What you do is that first, you take out the RL and replace with a short circuit like this. So define the short circuit current ISC to be the Norton equivalent current. apply any preferred method to solve for ISC. So you get, then the Norton current is IN equal to ISC, so you get this. You use the what do you call it, mesh analysis or nodal analysis or any method suitable for you. Example. Find the Thevenin equivalence resistance seen by the resistors RL in the circuit. Compute the Thevenin voltage and Norton current where RL, when RL is the load. Okay? So you have this. So now we need to find the Thevenin equivalent of these circuits. So what is the first step? The first step is that you find the R Thevenin by here. So what do you need to do? You need to take out this load, right? Remove the load. Second, you zeroize the source. You short the voltage source and open the current source. So you get that, this circuit. From here, you can see that 0.5 ohm parallel with 0.5 ohm here, and it's actually in series with 0.25 ohm and 0.5 ohm. So you get the R Thevenin of 1 ohm. So that is the first part, Thevenin equivalent resistance. Second part that you need to find, compute the Thevenin open circuit voltage and Norton short current. Norton current when RL is the load. So the second part is that we want to find the Thevenin open circuit. So what do you need to do? You take out the load and you find the open circuit voltage here. So you can use whatever method. So in this method, it uses the nodal analysis. So for the V1, for the node 1, you get 3 minus V1 over 0.5 minus V1 over divided by 0.5 and minus V1 minus V2 over 0.25. So you get this equation. And for the second one, second node, you get this node, V1 minus V2 over 0.25 minus 0.5 equal to 0. Then you get this equation. So V1 equal to 1.375. So therefore V2 equal to V2 is equal to 1.25. Okay? So V open circuit is basically equal to V2, so 1.25. Okay? So this is actually V Thevenin. Now, if you want to find the Norton current, so we have to replace the load with a short circuit. So this part, this I short circuit. Now we can use a voltage. Nodal analysis. We can also use mesh analysis. For this example, we use a mesh analysis. So you have 3 meshes: IA, IB, and IC. So IC is actually the one that we want to find, the I short circuit. IC is equal to I short circuit equal to I Norton. So from the first mesh A, you get this equation. So you get IA equal to 0.5 IB plus 3. For mesh B and C, for this mesh, you get this equation. So for the current source, you get IC equal to IB minus 0.5. You can go through this on your own. So yes, you substitute, therefore, all this, you find that I short circuit equal to IC 1.25 amps. Okay, so that is your solution for this equation, for this question. So, from the, what do you call it, what time is it?
12:34, sir.
12:34. Okay, so source transformation. So now you can see that the Norton theorem and the Thevenin theorem just now. So you can see that we can represent the circuit is using Norton or Thevenin. If it's Thevenin, is a voltage source, and Norton is the current source. Whereas the resistance, the R Thevenin and R Norton are the same. So therefore, there is a relationship between the voltage, V Thevenin and R, the I Norton. So through this relationship, we can transform the voltage source into current source and current source into the voltage source. So therefore, you can transform the Norton equivalent circuit into Thevenin equivalent circuit. So this is what we call a source transformation. Actually, it's a procedure that may be very useful in computation of equivalent circuit. So by replacing of current source with voltage source or vice versa. So the Norton and Thevenin theorems state that any one-port network can be represented by a voltage source in series with a resistance, or by a current source in parallel with a resistance, and that either of these representation is equivalent to the original circuit. So we can use this Norton theorem and Thevenin theorem to do source transformation. So like this, if you have a one port like that, remember we have a load here, so we can take out the load, and this one port network can be represented either by Thevenin or by Norton. And this value is the same in this circuit. So therefore, there is a relationship between Vt and In. So that relationship is this. Vt is equal to Rt In. So any circuit in Thevenin equivalent form may be replaced by a circuit in Norton equivalent form, provided using the following relationship. So by using this relationship, we can transform these two circuits, vice versa. So if you want to use the V Thevenin, so therefore, let's say if you want to transform Norton into Thevenin, then Vt here is actually Rt times In. If you want to transform Thevenin to Norton, so therefore, In is equal to V Thevenin over R Thevenin. So use V equal to IR, or I equal to V over R. So you can use that here. So this is the effect of source transformation. Basically, for example, you have these circuits, Vs, R1, R2, and R3. Okay, so this part looks like a Thevenin circuit, right? You have a voltage source and a series resistor. So this you can transform into Norton form by using Vs over R1, so it becomes the voltage source, and R1 is in parallel with this. So when you see this, you see this can be simplified, right? V1 parallel and R2, R1 parallel R2. So you can use this source transformation in simplifying your circuits. Example, you need to find the I1. So this is the circuits given. So you recognize this is really like a Norton equivalent circuit. And this Norton equivalent circuit, you can change it into Thevenin by using the formula. So you can change into this. So this value stay the same, but this current source is actually becomes voltage source. How? V equal to I R. I is 1 amp times R is 10 volts. So becomes like this. So when it becomes like this, you see this can be combined in series. So becomes this. 10 plus 5, 15, and with a 10 volt source. And this is actually a Thevenin. Thevenin, this is actually Thevenin here. Then this actually you can change it into a Norton, like this. And this also become Norton. And we can see here, from here, 15 and 5 is parallel. You can combine. And this, you can add. So become here. Become 8. And this parallel become 15 over 4. So this is a Norton equivalent. You can change into Thevenin equivalent. So finally you get this. Then you can find the current flowing through the I here, because we want to find this. So you can just use the voltage divider. So I is equal to that. So by using source transformation, you can also solve your circuit problem. Okay, clear?
Yes, sir.
So this is the maximum power transfer. I have another 2 slides to finish for this chapter. So the maximum power transfer problem is easily formulated by considering that the power absorbed by the load is given by PL equal to IL square RL. So this is the power to the load. And that the load current is given by IL equal to VT over RL plus RT. So we use the Thevenin equivalent circuit. Say from here, transform to there. Then basically that you can see IL is equal to VT over RL plus RT. So we can replace IL into that equation with this form. Okay, this combine the two expression. The load power PL is equal to VT square over RL plus RT square times RL. So therefore, in order to have a maximum power transfer to the load, your load must be equal to the R Thevenin. When load is equal to R Thevenin, therefore you get a maximum power transfer to the load. Any value you will not get. Other than that, you will not get a maximum power transfer to the load. Okay. Example. Equivalent circuit has a VT equal to 12 volt and RT is equal to 8 ohms. If the condition for maximum power transfer exists, determine the value of RL. So what is the value of RL? So the value of RL for maximum power transfer must be equal to RT. So RL is equal to 8 ohm. So the power developed in RL is how much? Use this formula and substitute the value of RL of 8 ohm, so you get 4.5 watt. So this is actually the maximum power transfer to the load. That's it. Any question?
Sir, do they give us the formula during the exam or we have to memorize it?
It depends.
All right.
Some we give and some we don't.
Okay.
Okay. Okay. No question.
No, sir.
No, sir.
Okay.
No, sir.
It's too much to cover, right?
Yeah, I need to do revision
Yes, sir.
again.
Yes, sir. Too much.
So tak apa, nanti kita pergi we go through the what do you call it, the tutorial. So I will give what do you call it, I will give this I will give a few next week. Today
Thank you, sir.
basically I just want to explain to you the theory behind it, and after that we'll do exercises. Right?
Sure, sir.
For tomorrow, I'm going to give you a small quiz on the similar to the first assignment, which is KVL, KCL, division, and Ohm's law, and so we call it resistors apa ni, series and parallel resistors calculation. Only that part, not the math, not the nodal analysis. Okay. Just
Yes,
a
sir.
short quiz tomorrow. Tomorrow is 1 hour, right?
Yes, sir.
Yeah. So most probably that the quiz is about less than half an hour. Right? So I give you what's about 3 questions, 3 simple questions. Okay.
All right, sir.
Any question?
Sir, when is the last due date for the assignment, sir?
Assignment. For the assignment 1,
Yes, sir.
submit lah.
Tak payah hantar, sir.
Jangan.
Kena hantar because that one carry marks.
Ini
Yes. It carry marks.
Minggu depan, sir. Minggu
Up
depan,
to you.
sir.
Minggu depan pun boleh. My assignment basically that the last date to submit the assignment is before the final exam.
Oh,
Okay, sir.
Oh, alright, sir.
Okay.
Before final exam, okay, sir.
So that is my what do you call it?
the style.
My practice is that the assignment is always before the final exams. But I give you the questions, what do you call it? Staggered lah. After I give lecture, then I give you the question for you to do. But in terms of the final submissions, is before the final exams lah. Right? So sometimes I will ask, okay, for this assignment, normally I will ask for you to submit the assignment before I give you the solutions. Okay?
Alright, sir.
Okay, so basically you need to be ready lah. Basically, when I said, okay, submit, because I want to give you the solutions, then you need to submit lah. So you cannot wait to do everything until at the end of the semester. No. When I give you have to do.
Last, sir. Alright, sir.
You need to do because it also helps you to understand. Any other question?
Sorry, sir. For tomorrow quiz, dalam handwriting ataupun Google Form, sir?
Handwriting, because it's some calculation.
Some question. And then we need to submit to
On,
MS team lah.
MS Team. Yes, you upload to the MS Team. What I'll do is that I prepare the question and I convert into PDF files. I put into the MS Team, into the assignment section in the MS Team, and I give you some time. So let's say, for example, the quiz is 30 minutes. I give you an extra 10 minutes for you to snap the photo, to convert to PDF using the captioner and whatnot, and to upload the MS Team. So I give you 10 minutes extra for you to do that. Then you submit. So in the MS Team, it will indicate whether you submit late or in time. I still accept submission, late submission, but there will be some points deduction. I don't reject your submission, but I deduct some marks. Okay?
Okay, sir.
Okay, sir.
Yeah. So for
Yes, sir,
tomorrow is the quiz is on the measurement on the units, on the definitions of, for example, let's say branch, nodes, mesh, loop, KCL, KVL, Ohm's law, voltage divider, current divider, uh, resistors in parallel, resistors in series, maybe some application, this kind of thing. Right? There's only 3 questions, right? So, okay, if you don't have any questions, then we can stop here. And hopefully you can, hopefully you don't have problems in answering the quiz tomorrow. Okay, thank you.
All right.
Good
Thank you, sir.
afternoon. Okay, good afternoon. So I'm going
Thank you, sir.
to stop
Thank you,
the
sir.
recording. Okay, thank you.